Okay, so great. I wanted to, first of all, thank the Cine organizers for inviting me to come and give this talk and inviting me to participate in the International Advisory Board. So what I want to do today is to tell you about some of the work we've done in understanding the operating principles of energy storage devices. Yesterday, we heard a lot about operando measurements, both for energy storage as well as for a number of other kind of technologies that are central to Cine. And I wanted to give you some idea of the way we kind of think about this, particularly in terms of battery space. So here's a really short outline. I'll talk a little bit about an introduction to batteries, just to give you an idea for how we think about this. I'll then talk about the importance of cell designs, and this is a little bit in the weeds, but based on some of the discussions we've had over the last couple of days, I want to give the audience a little bit of an idea, and particularly the students and postdocs who are here, kind of the way we think about this and what requirements are needed in order to do a truly meaningful operando measurement. I'll then talk about two rather different kind of technical areas. So one is very much a molecular level picture, so very much on the fundamental science side of understanding electrochemical interfaces. This is relevant not only for batteries, but also very relevant for supercapacitors, and that's one of the reasons I chose to talk about it. I'll also tell you a little bit about some recent work we've done in understanding what is potentially the next generation of cathodes for lithium-ion batteries. I'll eventually get this. The so-called lithium excess cathodes, and then I'll finish with a summary. We heard a lot about motivation yesterday, and I don't really need to go into details on this, but the goal in this is to drive down costs and drive up reliability so that hopefully everybody in this country will be able to afford Teslas, and we can get rid of or start to eliminate or start to electrify the vehicles. So here's a picture of a battery. This is an actual 18650 battery that at least some of the EV manufacturers use. But if you start to kind of dig down a little bit deeper, you can see that it consists of a number of layers. So here are the kind of active layers, the anode and the cathode. If we blow these up, here's the anode, say, here's the cathode, here's the electrolyte that separates them. Lithium ions go back and forth, and then electricity or electrons go between the two electrodes. If we blow up the different layers here, the anode and the cathodes, they actually consist of these large so-called primary particles. And then inside of each of these primary particles secondary particles are the primary particles, which are basically small crystallites or single crystals. If we then blow that up in more detail, these actually consist of atoms that are bonded together in some way. And so we need to understand oxidation and reduction kind of across these length scales. Because my talk is limited to 45 minutes, I'm going to focus on two aspects of that. One is what happens to the bonds and the atomic arrangements within the cathodes in these lithium excess materials, and then what happens to the electrolyte when it's in contact with the cathode. What happens right at that interface? So this is another way to kind of think about this, right? I talked about the range of length scales. There's an associated range of time scales as well. And so we are developing and are implementing a variety of ways of kind of controlling and understanding this. That has to do with the synthesis and fabrication over the range of these length scales. The characterization, again, over a range of length scales. I'm going to focus in this talk primarily at these shorter length scales, more on the order of atoms. And also very important, and it will be intimate to both of the technical parts that I talk about. Modeling and analytics is extremely important to be able to kind of link all of these areas together. So as I said, I wanted to say a few words about operando kinds of measurements. So it's good to start with a definition. So I'll start with a definition, and then I'll give you some examples of how we do this. So first of all, we use X-rays because they are very strongly penetrating. They easily go through whole cells, and I'll show you an example of that in a moment. And as a consequence, to do an operando measurement in an actual environment, that provides a great deal of advantage. So by operando, I mean here during operation. So here's kind of an example. So this is an actual pouch cell that actually was made at the Argonne lab. This is an example of a measurement that we've done on that pouch cell. The details don't really matter, and I don't want to go into them at this point. But this measurement was done kind of as we're actually cycling the battery. So this also allows me to introduce kind of a cycling curve. So this is now the capacity as we, in this case, start to charge up the battery, and this is the voltage across the anode and the cathode. And the curve then marks out what the voltage is as a function of capacity. These are done at different rates. So C over 5, if you look down here, is basically charging or discharging in 5 hours, where 6C is charging or discharging over an hour over 6, or about 10 minutes. And so while we walk along this curve, we're able to take this kind of data. It's operando because this is a real cell. We're actually able to measure a meaningful device performance. In that case, the cell voltage as a function of capacity. So that's my definition of operando. In contrast to that, and still highly relevant, is what we'll call in situ, which in this case means in a relevant environment. So here's an example, and this contrasts to the operando. So this, and I'll show you some data from this, is an example of a little cell we've made where we have a lithium counterelectrode, a copper, the data won't be from copper, but some kind of a working electrode in a cell that's basically flooded, so it looks something like this. The advantage of this is the environment's relevant, but it allows us to do measurements that are still highly relevant to the context in the context of energy storage. And then last, and equally important, is what we call ex situ, which we basically take this battery, or we take this battery, we disassemble it safely in the glove box, and then we'll do a more sophisticated measurement on that. This is useful because some measurements you can't actually do in a liquid environment. Those, from my end, typically involve soft X-rays, anything that involves electrons as well. And so, and I'll show you examples of this. In some cases, this is an extremely important kind of measurement that's necessary to do. So here's a couple of examples of some cells that we've developed. So this was done by one of my postdocs, Chris. So basically, we take a conventional pouch cell. We then sandwich it here between two holders. These holders are made of beryllium and coated on Kapton on the various sides. The advantage of this is we can actually apply a meaningful pressure to the cell, and then that allows us to do meaningful measurements, and I'll show you that in a minute, while we can collect, in our case, typically X-ray data. These are, again, in real time, and at least for most of what we looked at so far, that tends to be reasonably slow on the minutes to hours time frame. So that's what, to go back, that's what it looks like. In reality, we actually have moved on from these clips to something a little more sophisticated. So this is an example, and this basically is a proof that the measurement, that the electrochemistry we're doing on the cell is actually relevant to the battery, to the X-ray measurement we're doing. So at the top now is this capacity curve, so voltage is a function of lithium fraction, while we're actually going through a charge and a discharge cycle for this particular cathode. And this is now done in a coin cell, and you can see the curve looks like this. These are the number of lithium ions we're able to extract or insert before we hit a voltage cutoff. And this is now in the pouch cell while we're actually doing the X-ray measurement. And you can look at these curves both for the first cycle here and for the second cycle here and see that they agree very, very well. There's some minor differences in terms of perhaps a nucleation barrier here, but this gives us a great deal of confidence that the X-ray measurement that we do is going to be highly relevant to the actual battery. So that's one example. I'm going to skip over these in the interest of time, but we developed a number of other different cell technologies that allow us to do this in a variety of different environments that are relevant to the energy storage device. Okay, so enough for an introduction. I'm now going to give you some idea of the way we kind of look at the fundamentals of electrochemical interfaces. This work was done by my former postdoc, Hans-Georg Steinruck, who is now a staff scientist, and my former graduate student, Chungtian Cao, who is now a postdoc. And here are a couple of citations if you're interested. So the idea is this, right? If you look at a liquid or an electrolyte, one way to kind of understand the arrangement of the molecules is to look at what's called the pair distribution function. So this is imagining I'm starting at this atom, how far do I have to go before I get the next atom? That's this peak here. And then how far do I have to go for the second atom, and so forth. And so this is a measure of kind of the local structure of the liquid, and it's very characteristic for kind of looking at the structure of liquids. And it has an intimate relationship to things like transport. But what happens to this if we put an interface there? The liquid will respond in some way, and that response is actually very important for supercapacitors because basically you're relying on the electrochemical double layer to give you the capacitance. And so this is actually basically, other way to think about this is the electrochemical double layer. And so if you want to understand how to develop a better supercapacitor, you want to understand how to change transport across an interface for a lithium-ion battery, we kind of have to understand how molecules arrange at these surfaces. And so the interfacial structure then is extremely important for transport and for supercapacitors. So we want to try to understand how to measure that, and so the approach that we've used is a technique called X-ray reflectivity. X-rays come in, hit a surface, they bounce off that surface at sufficiently low angles. Let's imagine we have a film that sits on that surface, so X-rays bounce off this interface, and they bounce off this interface. There's a path length difference between those X-rays and these X-rays. And so you can get interference between X-rays that bounce off here and X-rays that bounce off there. And that interference is highly sensitive to kind of the thickness as well as the density of this. So that's kind of a very simple case. And so this is the typical reflectivity curve you might get. So this is now the log of the reflectivity normalized to the incident X-ray, so the number of X-rays in this, as a function of basically this angle or something that's proportional to that angle. So the black curve is imagining just a thin or a flat silicon layer with an electrolyte on top. You put this other layer on the top, and you see these interference fringes that give you some insight into things like thickness and electron density. And then the roughness basically helps to damp this. So this is a very well-established technique. I've explained this in a rather simple case, but you can actually think about this as a more general case of an interface kind of as well. And typically, I'm going to plot the reflectivity as normalized by the so-called Fresnel reflectivity, which is basically this flat curve, this black curve, which is from a flat interface. So we wanted to try to start to develop ways to go after this. We're going to start by looking at this conventional ethylene carbonate, dimethyl carbonate in lithium hexafluorophosphate. As we vary the salt concentration. This kind of gives you the size of the molecules, which will be important kind of a little bit later. Basically, they tend to be long and a little bit narrower kind of across the molecule. In this case, we're using a rather an interesting substrate. It's sapphire, it's an insulator, you can't actually charge it. But these are kind of the first steps to now go into substrates where we actually can apply a bias. And those experiments pretty much are ongoing now. This shows you the cell. So this is actually the same picture of one of the cells I showed you earlier. So this is what I would call an in situ experiment. You can't really see it, but there's lithium that sits out here, and the substrate, in this case, the sapphire sits down there. And then we go ahead and do the measurement. X-rays come in this way and come out that way, and we'll detect that with a detector. So here's the data. So this is now the reflectivity normalized by the Fresnel reflectivity, basically make the curves a little bit flatter as a function of incidence angle, as we go from basically no salt up in salt concentration. And you see there's kind of a pronounced dip and a pronounced maximum in here. If you go back and think about this constructive and destructive interference argument I made, if we look at the dip, that immediately tells you that you have some kind of structuring with a quasi-periodicity of around 4 angstroms. We look at this, 4 angstroms is just about the same size, the same width of the molecules. So what you immediately tell is the molecules are laying flat on the surface. And you can also see that as we go down, up in concentration, this dip in the peaks tend to get more pronounced. So the higher the salt concentration, the more order you have in the interface. You can also, if you look very closely, you can see there's a small shift in the minimum spacing, which means that as we go up in concentration, there's kind of a shift in the spacing between the layers actually going up a little bit. So we've modeled this. I'm not going to go into the details of the model, but we basically model this as a sequence of layers. So here's the first layer, the one that's adjacent to the substrate, the second layer, and then subsequent layers. So if you look in kind of a simulation, they would look something like that. It gives rise to basically what we get. So this now is the reflectivity in the symbols, and the lines are basically this model that I just went over very briefly. And this is basically the density profile that we get out of that. So on the left side over here is the substrate. This is the sapphire. And on the right side over here is basically the electron density of the electrolyte. And here's the first layer of the organic electrolyte that's next to the surface. Here's the second layer, and in some cases you can kind of see the third layer moving into the bulk. So if we take this region and blow it up and basically subtract out the substrate, this is what we see. So again, first layer, second layer, third layer, and in some cases fourth layer. And so now you can actually see the increase in ordering as we go up in concentration, going from the darker curves to the more purple curves, and the layering goes out higher. And if you look carefully, you can actually see an increase in the spacing between the layers, say between here and between there, as we go from the lower concentrations up to the higher concentrations. So that's great, but how do we start to understand it? And this gets back to one of the earlier comments that I made, that kind of having a computation in part of this is very useful. So we collaborated with a couple of theorists at the Army Research Lab, and I'm not going to go into the details of this, but they were basically able to do a molecular dynamics simulation. In this case, they were actually using a graphite surface, but the same, basically is pretty much the same electrolyte that we were looking at. So here's the graphite, here's the first layer molecule, second layer, third layer, fourth layer. So what they see then is consistent with our observations that both the EC and the DMC tend to lie flat on the surface. You can see that if you look carefully here. But the shorter axis, the axis of some of these kind of quasi-planar molecules is not well oriented. It actually tilted a little bit. They also seem to see that if you look in the salt, the lithium is pretty much uniformly distributed, where the PF6 anion seems to be concentrated in the layers that are associated with both with the organic electrolyte. Okay, so that's great, but one of the advantages of this is we can basically take this simulation and directly compare that to our experimental data. And so that's shown here. So the red is the data we just took, and the blue is the molecular dynamics simulation. We had to kind of adjust for the roughness in the substrate in getting the MD, so that's why some of the peaks are a little bit kind of smeared out. But if you look at this carefully, you see there's incredibly good agreement between the MD and the X-ray reflectivity. Remembering that the experiment was done on sapphire and the MD was done on graphite, what that suggests is that the arrangement of the molecules in this electrochemical double layer is mostly determined by the interaction between the molecules. And that the substrate list in this case has a reasonably small impact. If, as we're going to do in the next steps, we start to apply potentials to this, that's likely to change very much because the potential will likely orient the molecules in some way. So in the interest of time, I'm going to kind of skip over this a little bit. But as I said, we see some kind of a systematic dependence on concentration. The thickness goes up. This is basically a correlation length, which measures how well the electrochemical double layer is ordered. So big eta means you have the molecular layering extending well into the liquid, whereas a small one would mean you have only a couple layers that are well oriented. So we see this, and you could see this clearly in the data, increase as we increase the concentration as well as an increase in thickness. We can kind of understand that, and I'm not going to go into details by the fact that as we increase in concentration, the lithium that's associated with a carbonyl group tends to take these molecules which are disoriented at the lower concentrations and orient them a little bit. That kind of pushes the subsequent layers out. Sorry about that. Pushes the subsequent layers out, giving rise to both this increase as well as the increase in order. Okay, so to summarize this part, what we've done is take some steps to understand the interface structure that's relevant to lithium-ion batteries, also as well as supercapacitors. We've looked at molecular layering, and we get some insight into what drives the layering and how that depends on salt concentration. So why does this matter? As I mentioned, this is basically electrochemical double layer. It is what gives rise to the capacitance in supercapacitors. But it's also tremendously important in things like electrochemical stability. There are some suggestions that in particular for highly concentrated salt concentrations, the arrangement of molecules right at the surface will have a profound impact on stability. You can actually kinetically stabilize certain interfaces which would not thermodynamically be stabilized. We also see, consistent with the simulation, a very strongly structured electrolyte. What happens is we start to go to a field I think remains to be seen. And then because of the difference in ordering, there's some suggestion that lower concentrations might allow increased transport because you have a less structured layer, which is presumably easier to disrupt. Okay, so what I'm going to do now is tell you about some recent work that we've also done in understanding anion redox and some of the lithium excess cathodes. So this is work that was done in collaboration with Will Xu, my colleague at Stanford and SLAC, and together with a number of graduate students, Kapil Lim and Will Gent, and a postdoc, Jihoon Hong. And it was recently published a couple of months ago. So here's the idea. So this is a plot now of the storage capacity as a function of different chemistries. So lithium cobalt oxide, nickel manganese cobalt oxide, nickel cobalt aluminum. So these are kind of conventional cathode materials that you typically find in your cell phone, or if you happen to have an EV, they would also be present in your electric vehicle. And so there are a couple of things that are important here. One is the red is the theoretical capacity, and the light blue is the practical capacity. We cannot extract anywhere near the theoretical capacity in both of those cases, so that's a problem. So that drives the need to go to what we're calling lithium excess or lithium rich cathodes. These have, a higher theoretical capacity, something like 50% higher than kind of the theoretical capacity of conventional cathodes. And they're also able to extract a significant more capacity, a practical capacity out of these. The other thing that's really important in this context is that these materials are actually cheaper. So here's the lithium rich or lithium excess cathodes compared to the conventional lithium cobalt oxide, as well as the nickel cobalt aluminum oxide. And you can see here that the cost is dominated by the cobalt. Cobalt's very expensive. There are also humanitarian reasons why you don't want to use cobalt. So that's one of the things that drives the migration from kind of this older material to the nickel cobalt oxides and eventually the lithium rich oxides. So the reason that we are not able to extract the complete theoretical capacity out of these is illustrated down here. So this is the layered structure that's typically found in the metal oxide cathodes. So in green, I'm showing you the lithium ions. They basically form a layer. The red is the oxygen, and you can't really see it, but the transition metals, which are coordinated to the oxygens, are shown in the blue layers that sit in here. So what happens when we go ahead and charge the battery is the lithium is extracted from the cathode and goes to the anode. And so the lithium that was in this layer basically now is taken out, leaving the structure to look like this. The oxygens are, of course, negatively charged. So you have two negatively charged layers that are next to each other. That's not particularly stable. So what happens is that the transition metals that were in this layer migrate out, and basically the structure falls apart. The other thing that happens is the Fermi level drops. You then the Fermi level drops down into the oxygen band, and so the oxygen now will actually form O2 gas and desorb from the cathode. That's an irreversible change that you can't get back. So that's the major reason why you don't see this able to achieve the full theoretical capacity. We can partly solve that problem by going to excess lithium. So this shows you basically the same picture I showed you before. If we now take that structure and where the transition metals sit, we put a lithium layer that gives rise to, if we're now replacing 1/3 of the transition metals in this by lithium, a structure looks something like this on the side and then looks something like this at the top. And that stabilizes this, the cathode to the release of oxygen. However, there's some issues with that that we're trying to understand, and that's what's going to be the focus of the rest of the talk. One is, well, what is the nature of this oxygen that gives rise to the oxygen redox? So the other thing that's useful in these lithium-rich materials is, and I'll show you this later, we get capacity or oxidation reduction from not only the transition metal, but also from the oxygen. And so this gives rise to a bunch of work that's been done about the nature of the, in this case, non-bonding oxygen that gives rise to the redox. There have been some suggestions that you're forming these kind of oxygen dimers or peroxide-like species. Some suggestions that these linear lithium-oxygen-lithium bonds are the one that contribute. We don't really know, and I'll talk a little bit about that. There's also implications in terms of voltage hysteresis and degradation. We're working on that, but I'm in the conventional materials, lithium cobalt oxides, lithium manganese cobalt oxides, but I won't have time to talk about that. Instead, I'll also talk about the cation disorder. So as I said, you have cations that are stuck in these transition metal layers. They actually will tend to go in the layer where the lithium had been, and that has some important implications in both the oxygen redox and stability that I'll talk about. And so we want to kind of understand what drives this cation redox and how do we control it. So we've done a bunch of work on this. I'm going to focus on the lithium iridium oxygen. It's a beautiful material. Unfortunately, iridium is one of the most expensive elements around. So it's not ever going to make a practical battery. But it adopts the same layered structure as the more conventional 3D transition metal battery, layered oxides. And so here's the lithium, here's the iridium in blue, and then the lithium again in green. So the crystal structures are similar, the same to the lithium excess conventional materials. It has extremely good electrochemical properties. The other thing that this allows us to do is to compare the 5Ds to the 4Ds, and I won't have time to tell you about the work. Together with work we're actually doing in the 3Ds is more conventional nickel manganese cobalt oxide materials. And we're also going to look at not only the pure compound, but also alloying this with tin, and that's largely motivated this paper that came out in Science about 3 or 4 years ago. And the rationale for this is this allows you at some level to be able to tune the anion redox. And so this basically demonstrates that. So this is now a plot of voltage versus capacity, plotted now in a little bit different way than I have been before. And for those of you in the battery community who are used to seeing this, I'm taking basically the number of electrons that come out and then dividing them by the total number of iridium atoms that are present in the structure. So if there's no tin, we have the full component of iridium. This is just kind of the conventional kind of potential capacity plot that you'd see. And here we see these two plateaus. These, and I'll demonstrate that, are actually both due to cation redox. There's no anion redox in this material. And that's in contrast to what was published in that Science paper. As we start to increase the amount of tin, you see the curves open up a little bit, and I'll show you this, but that opening up, or the additional kind of capacity you get per iridium atom, is all due to the anion redox, and I'll demonstrate that for you kind of in a few minutes. You can also see kind of the loss of capacity and the voltage decrease on the second cycles, which is an interesting topic, but I won't have time to go over that. So how do we conclude that this is all anion redox? So again, we use this operando cell that I showed you before. I don't have the capacity data that we have in this. We will now do X-ray absorption spectroscopy at the iridium L edge, and those data are shown here. So this is now done as we're charging the battery, as we're walking up through here for the pure iridate compound. The blue marks the white line peak, or the peak in the spectrum. At the discharge state in the red and the charge state, there's kind of you can look here and see there's a continuous shift. We can look at that in more detail, and so that's shown here. So the bottom plot now is for the pure iridate. Here's the capacity plot, and here's the white line peak. We see it go up continuously as we charge and then go down continuously as we discharge. This is not a real sophisticated measurement. We've also done principal component analysis that's consistent with the fact that the cation is going from a formal oxidation state of 4 here to a formal oxidation state of 5.5 here and then back. In stark contrast to that, for the higher tin concentrations, we see very different behavior. So typically we see the white line goes up and then it basically plateaus or perhaps goes down a little bit. So all of the cation redox is in here before you get to this second kind of plateau here. Same, that's true at 0.25. It's also true at 0.5 where we see the cation redox here and then no cation redox after that. So what this shows then is that my picture here is correct. We see cation redox on this side, but I have not demonstrated to you that we see anion redox on this side, and so let me do that now. So a conventional way of doing this is oxygen edge X-ray absorption spectroscopy. So basically X-rays come in, they knock an electron up to a higher level, it falls down, you collect as the electron falls down, it gives off X-rays and you collect that. And then you do that as a function of incidence angle. And that's basically X-ray absorption spectroscopy, so it looks something like this. So these are real data. So this is for the pure iridate, pristine, partly charged, fully charged, discharged, partly discharged, and fully discharged. I'm not going to go into the details of this except to point out that because of hybridization, strong hybridization between the oxygen 2p and the iridium 5Ds, interpreting this is very, very difficult, and so it's actually it's challenging to get oxygen redox information from this kind of a measurement. So what do? Instead, we turn to what's called resonant inelastic X-ray scattering. Basically, it's the same process as X-ray absorption, except now I'm energy analyzing the X-rays that come off. So basically, you have an electron that sits out here. It's going to drop down into a variety of states down here, and depending on what state it ends up in, it will give off an X-ray with a different energy. And so we will energy resolve those and then for a given incidence angle, collect the energies of the X-rays that are emitted. And so that plot is shown here. So this is excitation energy, the energy of the X-rays coming in. And this is emission energy, the energy of the fluorescent X-rays as they come off. And so the X-ray absorption spectrum I showed you is basically the integral across here. And that gives rise to this. But this kind of a spectrum is much richer. You have peaks that can kind of appear in here that are very useful information. So some work that we published a couple of years ago on the nickel manganese cobalt oxide kind of demonstrated the value of this. So this is for the nickel manganese cobalt oxide in its pristine state, in its charged state. And if you look here, there are some kind of subtle changes that were reflective of the X-ray absorption spectra I showed you before. But strikingly, as we go to a charged state where we are activating the oxygen redox, where the oxygen becomes oxidized, you see the presence of this very strong peak that occurs here. And then when we discharge the cathode, that peak basically goes away. So this peak basically is the strongest indicator and the clearest indicator we have of anion redox. And so we can use this as basically a fingerprint for anion redox. And so now if we go back to the iridates that I was telling you about, these are now the Rix spectra. So again, excitation energy, emission energy at a various number of different states. So this is pristine. This is partway through that plateau I showed you about before. So this is purely cation. This is also, according to my hypothesis, purely cation. And you see here, clearly there's no peak that appears here. If we do a line cut across here, that's shown here. So this is emission energy, and this is intensity taken somewhere right in here. The peak would show up here, and it's clearly not there. So now, if we look at the tin compounds, the tin alloys, where I was claiming that we do have anion redox, we can look at the discharge. We can look at the fully charged state for the 25% and the 50%. If you look at the 50%, you clearly see a peak that appears in the raw Rix spectrum. If we again do this kind of integral, up this way and plot this as a function of emission energy, we see this peak has clearly appeared. If we look more carefully here and you stare carefully enough, you see there's a peak that sits here. The integral across here basically gives rise to the same thing, so you see this peak that sits in here. So what I've done then is to basically go back and prove this picture for you that we have for the low tin concentrations, we have only cation redox. As we go up in tin, we start to activate then the anion redox. So what this has done is show you that by alloying, we now have a handle or a way of controlling the anion redox. But I haven't addressed the question then of what gives rise to this. So in order to do that, we've done a series of structural measurements, which I won't really go into. It involves basically conventional X-ray diffraction, some neutron diffraction, and some so-called pair distribution function, which I will discuss briefly. But I'll just tell you the results of this, and so that's shown here. So this is now the ordered structure, or the structure in all of these materials kind of in their pristine state. I haven't shown you the lithiums, but they basically would sit down here. And here's the transition metals. The lithiums would sit here in kind of the holes. So you can think of this as being the perfect ordered structure after we had fully charged the battery. As I told you before, because you have these oxygen ions that are basically unscreened by any cations in between the layers, this is a highly repulsive and very energetically unstable situation. So what happens is that some of the cations that were sitting, either the iridium or tin cations that were sitting in this layer, hop down into this layer to help this try to stabilize the structure. And so you end up with a picture that looks like this. I'm not going to show you the data, but we've correlated that the amount of what's called transition metal migration with the amount of tin, and it's also correlated with the anion redox. But what you end up with a disordered structure that looks something like this. So let's imagine that this particular cation had jumped down into the layer. So what you do is leave behind a vacancy. It turns out it shifts over a little bit. But what we do is leave behind a vacancy here where this cation had been sitting. And so the oxygens that sit here now are in highly unstable configurations, and I'll talk about what happens to those in a minute in kind of the next slide or two. But what we've done then is to correlate the concentration of vacancies or the concentration of the transition metals that have migrated into this lithium layer with the extent of anion redox. So this is now for the pure iridium compound. We look at the pristine structure. We look at the structure cycled to high potential and then cycled down to low potentials. We basically, within a couple percent, see no transition metals migrated. And so it turns out that this, because of the high oxidation state of the iridium, we're able to kind of stabilize this layer, partly stabilize this layered structure in the pure iridium compound. In contrast, when we start to alloy in tin and turning on the anion redox, as you see here, we start to see a significant fraction of the cations in this layer moving down in between the two layers into what had been the lithium layer. So transition metals that have migrated to somewhere attuned around 10%. And there are kind of two types of these. And that turns out to be quite important. So there's this type, which is if I'm a transition metal here, I jump down to the layer beneath it. But if you look here, those also can be disordering by this transition metal moving into there. And that can also give rise to disorder the formation of vacancies. If this transition metal moves there, you're going to leave a vacancy behind here. And so this, and I don't have time to show you that, is strongly correlated to the extent of anion redox, both in this iridium compound as well as in the nickel cobalt oxide that we looked at as well. And it turns out that in order to kind of quantitatively give rise to this anion redox for both this compound and that compound, you kind of need to have 4 electrons per each vacancy that you're making. So I'm going to go through this reasonably quickly because I'm kind of running out of time. But as I said at the outset, in order to kind of understand a lot of these materials, you need to make use of theory. So we turned to Gerd Ceder's group for help with the theory. And what they were able to do is to give us insight into the bonding environment that's due to basically this transition, this cation migrating to the layer beneath it. So this is the local bonding arrangement, kind of in the perfect state with no defect. If this migrates to the layer beneath it, it leaves behind a vacancy. And so what happens is you see a shortening of the iridium-oxygen bonds from what had been about 2 angstroms to about 1.8 angstroms. And then a lengthening of the 2 other bonds that are kind of on the other side and coordinated to other transition metals here. And this shows kind of a sideways cut of the same picture. So that's great, that's theory, but do we have any evidence that that's actually the case? So to do that, we turn to what's called this pair distribution function measurement. So this basically is a way of understanding a local environment around, in this case, iridium atom. And I'm not going to go through the details of this, but if you look here, this first peak is basically all iridium-oxygen bonding. And so what we see is we go from the pristine case to the fully charged case, as you see a little bit of an increase here and here. So these are the short bonds that I told you I think we have, and these are long bonds that I told you I think we have. There are other possibilities. So this is one mechanism for the anion redox. These short bonds, basically they're singly bonded iridium to oxygen. This can give rise to oxygens that and I'm not showing you that again, that the DFT shows contribute to, that can be oxidized. There's another possible configuration which involves kind of very short oxygen-oxygen bonds depending on which transition metal migrates and how it migrates. And so I think we have some evidence for the first case, but not so much evidence for the second case. Okay, so to kind of summarize, I've talked to you a lot about the iridium tin, how we see this vacancy mediated oxygen redox. There are a couple of suggestions as to what this could be due to. We have some evidence for this. Not clear we have any evidence for this. What this does is split the state leading to the depopulation or oxidation of the oxygen. We kind of see similar behavior in the 3D transition metals, nickel, manganese, cobalt, oxide. And so I addressed a couple of the questions that I set out at the outset. We can control the oxygen redox with chemistry. We don't really know quite yet which of these 2 environments are the important ones. And perhaps most importantly for this audience, what I've done is demonstrate a methodology that one can use to understand some of these more complicated cathode materials. Okay, so for a high-level summary, again, what I've done is given you both a molecular picture of ordering at electrochemical interfaces, electrolyte ordering, talked to you about anion redox, and also, I try to give you an insight into our approach to basically using a combination of operando, in situ, ex situ measurements to understand chemistry and structure, and then relate that with very precise electrochemistry. And last, I should thank the funding agencies. This was partly funded by the US Department of Energy Hub, by the Vehicle Technology Office, some internal funding. All the measurements were done at either SSRL or ALS. I've worked extensively with Will's group at Stanford and Gerd's group at LBL, and we collaborated with a number of other people, both at LBL and at the Army. And so last, thanks for your attention.